Okay, so this is the very simple vehicle we're going to use. We're going to lift it up out of the water, maintain a steady altitude, and maintain stability and roll and pitch while doing that, all while using just 4 Dedi blades in a single Lua box. Now, in order to control Dedi blades with a Lua controller, you do need to know the index of the Dedi blade and the spin rate. And we can figure out the index just by testing the spin function. And then remember, the update function is the default function that runs 40 times every second. So inside this update function, everything is going to be called continuously 40 times a second. So in here, I will have just the function to set the spinner rate, set spinner continuous speed. We need the index, and indices in Lua start at 0, and so if we have 4 spinners, we'll have 0, 1, 2, and 3. So I'll have index 0 and give it a value to spin at, value of 1 for now. We can go from -30 to 30, so 1 will be just a slow spin, just to make sure it's working and to see what index 0 was. Here we can see our back left spinner is at index 0, so I'm going to go ahead and create a variable back left. And this is going to be the variable for that spinner's spin rate. We'll calculate it later, but for now I'm setting it to 0, and then I'm going to have that variable set to our spinner here. I'm going to do this for each of the 4 spinners at index 1, 2, and 3. And we'll start by setting just 1 to 1 and check what the index for 1 is. So back, that would be the back right. And I'll set this to the back right. And then we'll see which one is at index 2. That's the front left. And then this should be the index for front right. And I can check that and make sure that works just by setting it to 1. And yes, it is. Okay, so now we can control each of the spinners, and we know which index they're each at. Next, we want to calculate what these variables are going to be, the spin rates. And the spin rates are just going to be the values we get from the PID for altitude, roll, and pitch summed together. So let's create basically what the PID values are going to give us for altitude, roll, and pitch. Altitude, let's set that to 0 for now. And roll 0 and pitch. So these are going to be the values we get from the PID, saying basically it's like the error of that altitude, or the error in your roll, multiplied by the proportional or the integral or the derivative constant multiplier, and then adding them together to get the right values for each of the spinners, but depending on if they're in the back or the right, or in altitude, they're all facing up, so they're all going to be positive. So let's go ahead and add these together. Altitude is always going to be positive, but then our roll and our pitch are going to be determined by where they are on the craft. If any of our spinners were upside down, then altitude would be the opposite. In fact, they'd all be the opposite. So our spinners on the right side will be the opposite of the left for the roll control. So I'm going to have a negative value here on the right side, and then spinners in the back and the left will be opposite. So I'm going to have a negative for the spinners pitch in the front. And if I save these, it's just adding zeros, so they again are all going to be set to 0. So now what we want to do is calculate first. Let's do, instead of creating the PID, let's just do a simple error, which would be a proportional controller with the p-value of 1. So we're just getting the errors in our altitude, pitch, roll, and pitch, and putting them in here, and it'll be the same thing as if we had ACB blocks controlling this. So what I want is an altitude error, and in order to get an error, I need a goal. So my goal, I'm going to create a section just called basic settings, And in here, I'll create something called aim altitude. And I actually want all of these variables to be local variables. I'm not sure that you have to set them to local, but they should be local, so just in case, we're going to set them to local. If they actually use global, it wouldn't run as fast. And there's no need for them to be global variables. So local aim altitude, we'll just set this to 30. It doesn't really matter, whatever you want your altitude to be. And then our altitude error is going to be aim altitude minus what our actual altitude is, because we want a positive altitude when we want our spinners to increase speed, which would mean that we're not quite at our altitude yet. So our aim altitude is higher than what our actual altitude is. So aim altitude and then subtract our actual altitude will give us a positive value, which will increase our spinners and bring us up. So our actual altitude is just the function get construct position. And this gives us the x, y, z coordinates of our ship in the world, but to get the actual vertical value is just y. So it's the y portion of that position. So now this we can check, make sure it's working. Should give us that we're negative 30 or very close to negative 30, because we're not at altitude, we're near zero, and we should get an error of about negative 30. And when we press this, our spinners are going to start spinning to get us up to that altitude. But remember, we have no control in roll and pitch yet, so we'll probably go out of control. So here we go. It is working. We are getting the correct error, and our spinners are trying to put us into the air. But like I said, we have no control in pitch or roll. So I'm going to lock that. And now we'll just go ahead and do the same thing for roll and pitch, get the error. And in order to do this, it's just get construct roll. And the issue with this function is it only gives you a value from 0 to 359. So what we really need is a positive or a negative value depending on if we're rolling one way or the other. And we want equal magnitudes. So we do have to change this function, or at least create a new function to give us the values that we want. And I'll show you what I mean. If I keep track of our log, if we log our roll value based off of this function, we'll get numbers between 0 and 359. So here I'm let it run. It should go out of control as long as I've not locked it. There we go. So you can see it was stabilized as soon as it started to roll one direction, but if it rolled the other direction, it saw an error of 360 degrees and went, oh my god, we need to fix this, and rolled the wrong way. So we do need to create this function that's going to fix this and give us the value that we actually want. So our function is going to be get error and take in an angle. And we'll first of all see if that angle is less than 180. If it is 180, then we know that it's correct, and it's actually giving us the angle that we want. And we're just going to return that angle. If it's not, then we know it's actually it's returning an angle that's higher than 180, and we actually what we want is a negative value. So let's say we're rotating at negative 10 degrees. We're going to get a value of 350. We want to turn that into negative 10. So I'm going to return angle minus 360. So if the value is 360, we should get 0, which is right. If the value is 350, we'll get 350 minus 360, which is negative 10. So now we're getting equal magnitude and opposite values depending on if we roll one way or the other. And I'm going to go ahead and use this function to give us the correct error in roll. Apply that, and now our roll is fixed. The problem with it's not stabilized because all we have is equivalent to a proportional controller where the p-value is 1. So we're just correcting by the error, which is similar to what an ACB block would do. But let's go in, and of course our pitch is not being controlled yet, so it will eventually go out of control. So let's go into our pitch and do the same thing. And literally it works the same way, except you're going to do get construct pitch. And now we can see, it's going out of control, probably because the values that we're summing here are actually the opposite. So I'm going to do a minus and a plus, depending on if they're in the front and the back. I'm just going to rotate those. Let's save that, and here we go. Now we've got a actual literal P controller, just a proportional controller working where that P value is 1. And just by getting the error in the angles and pumping that right into our spin rates. So that's the simple way to create a P controller. Now we're going to go in and we're going to create the actual PID function. And that's going to return the values we really want for these to keep it more stable than it really is now. And in order to create a proportional controller or a PID controller, you do need to store values. So I'm going to create tables to store these values. And I'll call this section Initializing Variables. And so I'm going to create a table of variables for each of the things we're trying to control, altitude, roll, and pitch. So I'm going to create the table altitude, and inside that table I need to have a p-value for the strength of the proportional, I-value for the strength of the integral, same with the derivative, and then we're going to need some other values in order to use the integral and derivative portions of this controller, because just a p controller is simply taking this value, this error, and multiplying it by altitude.p, which is this p-value we're going to put in this table. And this will give us literally a proportional controller where we can control the p-value and the strength of that error value into our spinners. And it works the same for the integral and the derivative, giving them the strength that they have to control the PID itself. And then the integral needs a couple of other constants. So it's going to need time, which is the time it takes for the integral to correct itself fully. So the amount of time it takes for an error to build up before that error kicks in and makes the integral start to make a change. And then we need the integral itself. And that should be all we need for the integral controller. The derivative controller is really simple. It's just the error we have now minus the error we had last time times the derivative constant. So I do need to store an error value, and that's going to be our past error. And that's all we need for our table. And we want a table for each of the settings we're going to control with the PID. So roll and pitch. And then we're going to go ahead and set some of these values right from the start. Call it PID settings. And some of these settings we're gonna change as we play with it. Each vehicle is going to be a little different. So first of all, let's change, or let's initialize the variable for our P, for our altitude. And for now, I'll just set it to 1. And we're going to do the same thing for the I, the D, and the time. So a value for I, let's do time here, and a value for D. Now time, you can use the CPU clock, you can pull what the actual time is and compare it, but that's slow. I'm going to do something you probably shouldn't be doing in coding, but in this case, it doesn't really matter because we can rely on this code to run 40 times a second. So I'm going to base it off the amount of times this function's being called. So this one will be called 40 times a second, and if I want something, say like 3 seconds, I just want to multiply that by 40, and that'll give me 120. So this will be a integral controller that takes 3 seconds to gain full power. And then the derivative controller, let's give it a value of 10 for now. I'm going to build this for each of the settings, altitude and roll. And one for pitch. Now I don't need to set the settings for an integral or the error. They're always going to start at 0, so I can just initialize those to 0 here. And so now we have the initialized tables we're going to use for each of our controls, and then the PID settings that we can change here to modify it and tweak it as we go. So this, let's just save that. Everything is good. Let's go ahead and create our PID function. Call it PID. And now this is going to take in one of these tables, altitude, roll, or pitch, and we're going to refer to that table as just X in this function. And then we do need an error, and I'll explain why later. Inside this function, let's start with a simple proportional controller and test it, and then if that works, we'll move to a derivative controller, and then we'll move to an integral controller and add them all together. So first of all, we're going to do apply proportional section, and in here we're just going to create a local variable, and we'll call this correction, because what a PID controller does is it takes in the error and it returns a correction to fix that error. So this is going to return our value correction once we've made our changes to it. So correction for the proportional controller is just equal to our error multiplied by our table's value for P. So this 1 here. And so when I return this value of correction, it should do the same thing as what we're doing here if I called it. PID for altitude. Error is the error that we were calculating. And let's do the same thing for roll and pitch. Call the table is roll. And then there's the error. And this one is pitch. And the pitch error. We run this, and everything stays the same because we use values of 1. Now the nice thing of what we've done is we're able to control our settings and the strength of our proportional with the settings here. So if I have a proportional in my altitude of 1 and I half that power, now I should drop and be have a harder time maintaining my altitude at 30. And you can see we fell now to 15 meters. If I increase it to 2, we should be able to go up and get much closer to our 30 goal. And we're at 27 or 28. So that's working perfectly. And so now we do have all of our settings here and our proportional controller working perfectly. So these settings were the settings we said we were going to get from our PID. We're going to add them together to get our spin rates, and then set those spin rates to our indices, depending on if they're in front of or to the right or the opposite of our center of mass. So the next thing I'm going to do is I'm going to create the derivative controller, because the integral controller is a little bit more complicated. The derivative controller is actually the part that's going to stabilize this, and the integral is the part that makes corrections where the proportional isn't quite strong enough or is constantly seeing an error. So I'm going to go in and create a section called Apply Derivative. And in here, we're just going to take this correction and add the derivative change to it. So the derivative is applying its correction to the controller. And that is simply just going to be the error now subtracted from the error we had before times that d value. But here's why we had the error argument to begin with, instead of just storing it in the table. Because what we want to do is store the old error in the table and use this error as our new error. So I'm going to create a new variable called local last error and set that equal to what our new error is going to be. Our new error is going to be stored in our table to be our last error next time. So this will be the error we had in our table from last time. And the new error is going to be the error that we have above. And so this will store it in our table, so next time we can have our last error. And so this creates the derivative controller where we can subtract our old error from our new error and multiply that by our table's d value. So now we have the correction of our proportional, and we're adding the correction of our derivative. When we apply, we stabilized. So we have what we've created now is a proportional derivative controller. There's no integral yet, but this is all you really need to stabilize something. In fact, this is all the PID blocks in from the depths use. I think they set automatically by default the integral to 0, at least it looks that way. But we can now create the integral portion. So what I'm going to do is go ahead and create a section for the integral. And this is going to be, it's going to look complicated, but what I really need to do is I need to create the integral itself. I need to store that in my integral section of my table. And in order to do this, essentially this is what the concept is over time, we're taking values of this error and we're adding them up and we're taking the average over all of the summations. And so basically our time is how many errors we're adding up, because time is running each time, time is being added by 1 each time update's running. So it makes it really simple to create an average of these numbers, of these errors over time, just by using time as our denominator. But then what we want to do is for each new function call, we want to take out one value from our integral. We'll take out basically the average. So we would take the average multiplied by the time, subtract that by 1, and then we will add our new error in, and then we'll take all that and then divide it again by time. So I'll show you what I mean. We're going to take what our integral is, we're going to multiply it, because what we're taking is an average of values, and the values there's time number of values in there. So we'll multiply it by our table's time value. And we're going to subtract 1 because we're actually removing 1 from it. because we're going to fill it with a new value, the new error. And then we will actually add correction and divide that by time. So actually what we want is, this should be error. This should be the current error. So this should be x dot error. There we go. So my notes are wrong. So what we want are our integral, which is, like I said, it's the average of all our values in time number of values, averaged out. So we're going to multiply it by time, and then because then we can subtract 1 and then go back and divide by time to get the average again after adding one more error to it. So this now becomes our new integral. And so we take this integral and we add it to correction. And of course we're going to multiply it by our integral's power, which is x to I. So this is our integral controller added in. If I hit save, you'll notice no difference because there is no large error for it to start correcting. The integral controller doesn't really do anything unless there's a large error for a very long time, in this case 3 seconds. But what I can do is test it to see if it's working, and that's by creating a constant error. So I'm going to weigh down one side of the ship, and you can see it's starting to stabilize itself. 3 seconds has passed. Let's go ahead and undo that and check it again. Let's let 3 seconds go by and add another error. And you can see after 3 seconds, it does everything it can to stabilize that. If it's not strong enough, we can increase it. So let's do a roll integral of 2. And let's apply that. And it should be doing a little bit better. It might be easier to show this by using altitude. So right now our altitude is maintaining a steady 27, 26. If I change my altitude integral to 5, now it's going to maintain that because there was a constant error. It was never quite at 30. Now it's a little too strong. The derivative controller isn't strong enough, but I'll change this to 2. And so what we see now is we should be able to maintain much closer to 30 because our integral controller is saying, oh, there's a constant error. I'm going to multiply that number we gave by that constant error, the average of it over time. Let's give my derivative a stronger number, my integral stronger, and let's get up to 30. Let's see if this can work. It's doing a little bit better. It's bouncing around, but you can see it is trying harder now to maintain the 30. We're getting to 29. So the integral controller is working. I'm gonna go ahead and place these back to where we were. And that's it. That's everything you need to know to create a PID using Lua box and Dedi blades. So just testing it again, let's go ahead and add a heavy beam to the front. You can see that the pitch is being stabilized and the integral is taking over, trying to prevent that from being a constant error. We can do the same thing and just add a bunch of weight. And you can see that as we get lower, the proportional controller is going to spin these higher, and then the integral is going to kick in over time. And that's it. So I hope you enjoyed this video, and I'll see you in the next one.